All right, so where we left off, we were just talking about the second law of motion, the fundamental law of motion, which is really F net equals ma. As we go on this week, we'll look at what I'm talking about down here, about doing the sum of the forces in the x direction and the y direction. But for right now, all that matters is that F net is equal to ma, which is the basic equation from the second law. Now notice it says that it will accelerate the object in the direction of the motion. So the F net and the A will always be in the same direction. That makes sense. If you're driving down the street and the light turns red, you step on the brakes, which puts a force in the opposite direction of your motion, and you slow down, which means your acceleration is in the opposite direction of your motion. When the light turns green, you step on the gas, which puts a forward force on your car, and you accelerate forward. So always, the F net and the A will be in the same direction. The other thing that's interesting to note is that the acceleration, if we rearrange the equation for acceleration, it's F net divided by m. So what it's saying is the bigger the mass of the object, the less the object will accelerate. So if we go back to the ball that I put a tiny little force on, or the textbook that I put the same tiny little force on, then obviously the mass of the textbook is much bigger, and so the acceleration is going to be much smaller. Okay? So we say that the acceleration is directly proportional to the force, but inversely proportional to the mass, meaning as the force gets bigger, the acceleration will get bigger, but as the mass gets bigger, the acceleration will get smaller. Okay, so that's the second law of motion, the fundamental law of motion, F equals ma. All right, the third one. The third one might be my favorite, just because it's the one that makes people stop and say, what? You use the third law all the time without ever even considering it. So the third law is known as the law of action and reaction. And so it says, just trying to make it a little bigger and clear. So it's the law of action and reaction. So if one object exerts a force on a second object, then the second object must exert the same force back on the first object. If one object exerts a force on the second object must exert the same force back on the first object. There is one key essential word in that law. If one object exerts a force on a second object and the second one must exert the same force back on the first, it is the word must. It doesn't say might or could. It must. If one object exerts a force on a second object, the second one must exert the same force back. If it doesn't, then the first object can't put that force on the second one. And something has to give. So think about whatever you're sitting on right now. Your weight, the force of gravity, is putting a force on that object. If you were in a kindergarten classroom and you sat on a little kindergarten kid's chair, it might be that that chair would not be able to put an equal and opposite force back on you compared to the weight that you're putting on it, the force you're putting on it. And if that happens, then the chair gives way and you fall. Okay? The same is true if I'm trying. Okay, think about. I'm trying to figure out how I can hold my thing. Okay, so think about me holding this piece of paper up, just like this, and I might say to someone, "Hit this paper as hard as you can." Well, they can haul off and put as much force into their punch as they want, but this paper will just move backward. The paper is not able to exert that equal force back, and as a result, no matter how hard the person tries to hit this paper, they are not going to be able to put very much force on it because the paper gives way. But if I were to hold this paper up in front of a cement wall and say to the person, okay, now hit it as hard as you can, they will certainly be able to hit the paper with all the force they want. They might break their hand, but they'll be able to hit the paper more. Okay, so that's what the must means. If the second object can't exert a force back, then the first object just can't exert that force on it. Now, it leads to some really cool things. For example, let's go back to that wall. When someone hits a wall with their hand, two things can happen. One might be that their hand goes through the wall, and it leaves a hole in the wall. Now, that might not be a good thing for the wall or for the person when their parents get home, but it's a good thing for their hand. Because if their hand goes through the wall, it means the wall doesn't have the ability to put an equal force back, and so their hand's not going to get hurt. But if they happen to be unlucky and hit the wall at a spot where there's like a stud, a beam in behind, some reinforcement, then the wall's able to hit back, to put an equal force back on their hand, so the wall won't be damaged, but they'll probably break their hand. So if you ever say to someone, oh, did you break your hand when you hit the wall? Really, the answer is no. My hand got broken when the wall hit back. Because if the wall didn't hit back, my hand would be fine. Have you ever thought about how you walk across the floor? It's Newton's third law. Right? Sorry. There's a reason I'm not teaching art. Okay, so this is supposed to be my foot. And I just didn't want to draw it right on the floor. Okay, so when I go to walk across the floor, this is my ankle. When I go to walk across the floor, I push down and back. I push at an angle. There's a component down and there's a component back. But why am I pushing backward if I want to move forward? Well, I'm pushing backward so then that the floor will push up and forward. Up so that I don't go through the floor, and forward so that I can move forward. Think about all those little kids learning to walk. They're doing physics in their head. They're thinking, okay, how much do I need to push backward? How much did I gain? How much mass did I gain since yesterday? How much do I push backward with? Like, they're doing physics. No wonder it's so hard for them to learn how to walk. And then, like, now that we're older, we don't really have to think about how much force do I need to push with so that I can safely walk across this floor until something about the surface changes. Like if the surface is slippery, if we're walking on ice, if it's wet, if it's dark and we're not sure, then we walk much more carefully because the force that's pushing back is connected to the friction of the surface. And so if the surface doesn't have friction, and I push with too much force, then the surface can't push back and my foot slides back. So I have to be careful that I don't push with too much force, because if the surface can't push back with that much, then I'm going to fall. It's kind of like if you're walking across like a swinging bridge, right? You can't push with as much force as you would when you were just walking normal because it can't push back with it. Have you ever thought, I'll just do a few more because we're going to run out of time, but have you ever thought about how you climb a rope? Right? So here you are, you're going to climb a rope. This is you, you're putting your arms up to climb the rope. What way do you put a force on that rope? You pull down. Whoever heard of pulling down if you want to go up? Well, you pull down, and it's the rope pulling back that pulls you up. So it isn't that you don't have enough muscle to climb the rope because you can't pull down with enough force if you want to try to make yourself sound better when someone makes fun of you. It's because the rope isn't pulling back with enough force. If you've ever fired a gun, right, the gun puts a force on the bullet, sending it this way, and the bullet puts a force backward, which causes the gun to kick back. And that's why sometimes we end up with a bruise or something on us. If you've ever been on skates standing on the side at a rink, right, you push in on the wall or in on the boards, and the boards push you back and you go out. Newton's third law is everywhere. It's also why when you're in bed in the morning and your parents are like, it's time to get up, It's like, I can't. It's not my fault. The bit isn't pushing back with enough